Good morning, everybody. Hopefully you're doing well. If you can give me a green check mark if you're with me, and we might have a few people trickling in as there's no homeroom this morning. Mrs. Ward, Mrs. Wood are at a conference, so they'll be gone for a couple days. So you're stuck with me, scary as that seems. First, I'd like to start with any questions you may have had from the work from the last couple days, Chapter 5 stuff. So if you have anything in terms of questions that you want me to go through, I'd be happy to do that. I'm hoping that this material, the first two sections, are pretty straightforward in terms of difficulty. There's not a ton of real hard stuff there. So if you have anything though, anything that's maybe a bit unclear, I'd be happy to go through it. I don't see anybody typing that in, so I think we're maybe okay. I want to pick up from where we left off last day, and we started talking about relations, functions, domain, and range, and I didn't spend a whole lot of time talking about domain and range. So we're kind of breaking up this lesson 2 into 2 parts. I don't know if I'll get through it all, but we'll see. Anna says the live screen keeps buffering. I'm not sure what that's about. Is anybody else experiencing that problem, or is it just Anna? Is anybody else having some buffering issues? The irony is they wouldn't even hear me say it if their screen was not loading properly. Might just be a bad internet day, your place, Anna. These things happen. Yeah, it looks like everyone's good. So, yeah, it does happen, right? And it's just dependent on your connection. Generally speaking, our end of things usually broadcasts out pretty well, and it's pretty consistent. And then at home, I know my personal internet at home isn't great some days, and some days it is. So, a couple things you can do, Anna, if you have anything else running in your computer, you might want to close it down. Anything using the internet, maybe your little brother streaming some movies and YouTube in the background or something. That's my only suggestion. I'm going to jump back to lesson 2 from last day, and we skipped a couple ideas of domain and range, and I want to talk about them more in depth today. So we're going to talk about domain, range, and how to identify a function or a relation just by looking at either a table or a data set or whatever the case may be. So, all right, so at the very end of the lesson, somewhere in here, we talked about domain and range, because at the very end we said the domain was all the x values, and then the range was all the y values. So this is the red at the bottom. So anything in the first set was considered our domain. Anything in the second set was considered our range. And we did some kind of, not silly examples, but examples with bicycles and motorcycles and wheels and things like that. So generally speaking, we're not going to run into a lot of stuff like that. We're going to probably more be dealing with numbers and graphs moving forward, but just kind of get you used to these ideas. So we didn't talk about the domain and range for the example of the city and then the territory it was in. So let's fill that out right now. Sometimes we use the letter D to represent the domain, and we can use these squiggly brackets. Here I have to concentrate to draw my squiggly bracket, and that indicates a set. So anything in the first oval was our domain. So in this case, we had Hay River. We have Equalite. A-L-U-I. And then is Civic. Old Crow. Yellowknife. And Whitehorse. So it seems pretty straightforward when we're dealing with just bubbles, or everything's just there for us. So it's kind of easy to deal with it here. For the range, anything in the second bubble, that's going to be our range, the second oval here. So we have Northwest Territories, Yukon, and Nunavut. Pretty straightforward. Nothing terribly difficult there, hopefully. X values, Y values. First bubble, second bubble. Domain range, that's kind of what we're going through here. So that was the first example there. And then when we scroll down a little bit, we did that one. What about the first one? Let's look at the very first one here. I know I'm going way back. When we talked about the color of the fruit and then the fruit. So in this case, I'm going to identify my domain and range, and I'm going to do the same thing as I did before. So domain gets a D, and domain is everything in my first set. So that would be my fruits here. Or if I want to think of it this way, it's everything in my ordered pairs that comes in the first half of my ordered pair. So we had apple. Apple came up twice. We only need to include it once. We have blueberry, cherry, and huckleberry. Is that? All right, so that was our first set. Then we had our second set, the range. Maybe I'll throw this in a different color. So these are all the second values, or the second column here up above. So what did I have? I had red, green, blue, red, and blue. So just red, green, and blue. Now, I don't need to include things more than once if they are written down more than once. There's just there, it's there, we just write it. So if blue appears, 100 times, you put it once, it's there. Just kind of taking account of the things that are there or aren't there. So that's domain and range, a little bit of a refresher from last day. We're going to talk a bit more about it here in a second. So on the very last page of your, I guess the first half of the learning guide, there was a couple sheets. They looked like this. State whether each relation is a function, indicate why or why not. And we never got to it last day, but I'd like to get to it now. So there is a test, and it's called the vertical line test. And if you went through the lessons in the course, the extra lessons that are there, the vertical line test, there's one of those little kind of game things there that shows up. And this is it. So I hadn't talked about it yet, but I'll talk about it right now. So I guess we should, I don't know if it's even worth writing it down. I'll show you the vertical line test, and then we'll describe it a little bit. So if we have a function, the vertical line will only hit 1 point. If we have a relation, it can hit more than 1 point. So if I draw a vertical line on this circle, number 1 here, is there somewhere I can draw a vertical line which will intersect that black line more than once? So let's take a vertical line. I'll draw it just kind of randomly right here. There we go. Did I hit the black line more than once? So I hit it right here, and I hit it right here. That means this fails the vertical line test, and it is a relation. If you remember back to the definition of relation and function, when we had a relation, I think we were looking at the first thing we did, we had a bicycle and a motorcycle, and bicycle gave us a value of 2, and then motorcycle gave us a value of 2 as well. So if we have something in our first set that gives us more than 1 in our second set, then it is a relation. And in this case, if we pick an x value, let's say we picked an x value of like 2 here, that gives us a y value up there and a y value down there. So this is not a function, so no. And the reason it fails the vertical line test So we'll look at the next example here, and then we'll kind of write down what this vertical line test is. So is there a vertical line you can draw, number 2, that will hit more than one spot on the black line? So it has to be a vertical line. It can't be, you can't have something on an angle like this, because that's not a vertical line. That's a line on an angle. So we have a line that goes straight up and down. Is there a line you can draw straight up and down that crosses that black line on that graph, that plot, more than once? Is it possible to do that? What do we think? No, I don't think. Yeah, let's see if we can find it. If I draw a vertical line here, I'm only crossing one. I can go wherever I want as long as my line is vertical. I'm only crossing at one point. So there's one crossing, there's one crossing, one crossing, one crossing. No matter where I put that vertical line, I'm only crossing the black line at one spot. So that means that this line is a function. So is it a function? Yes. And why is it a function? Because it passes the vertical line test. All right, so we have an example of a relation, fails the vertical line test, a function passes the vertical line test. We should probably write down what this whole vertical line test thing really means. So I'll write it up here at the top. You probably have some room in the header. Vertical line test. If you can draw a vertical and vertical is very important line which crosses your plot only once, then you have a function. Starting to think I don't like my definition, because it's not always going to be true. Let's, I'm going to erase the end of this. Hopefully you haven't gotten this far. I'm going to do the inverse. I'm going to kind of go backwards. So if you can draw a vertical line which crosses your plot more than once, then you have a relation. So the key thing is here, your line must be vertical. You're going more than once, so twice or more is a relation. All right. Let's continue on with the next couple examples here. There's 4 more. And I want you to kind of think about the 2 examples we have up above and see if you kind of replicate those on the next 4. This isn't meant to be like a super difficult idea, so how are we doing on it? Are we kind of getting it or not really want to see more examples? Throw it into chat there, let me know how you're feeling about it. So a vertical line, if you can intersect your plot more than once, it's a relation. If you can only draw, or if your vertical line only hits once, then it's a function. Alex thinks she's getting it. Got a thumbs up. Taylor, pretty good. Okay, I just wanted to make sure because it was kind of quiet in here and I didn't know what was going on. So let's continue on. Let's look at a couple more examples. Number 3 here. Is it possible to draw a vertical line that intersects that black line more than once? And this is kind of like number 2. No matter where you put that vertical line, you're only intersecting once. So I can put it there, I can put it there, I can put it there. It doesn't matter where it goes. You're only intersecting one time. So this is a function, yes, and it passes the vertical line test. Or we could write something like vertical line only intersects once. Okay, excellent. Number 4 is tricky. And this is one that kind of gets students now and again. What do we think for number 4? Is that going to pass the vertical line test or is it going to fail the vertical line test? It is a vertical line in itself, so what do we think? Function or not? Let's go with that. Function yes, function no. Votes are coming in. Fails, fails, function no. Not a function. I think you guys are maybe just too smart for me today. Usually this one trips everyone up and they look at it and they think, well, you know, if I draw a vertical line here, I haven't intersected more than once, no more than once, no more than once. The problem lies when you take a vertical line. I don't know if I'm going to be able to do this with my tablet, but yeah, it's kind of working out all right. If you put your vertical line right on the vertical line, technically speaking, you're intersecting that line at every single point. So it's hard to see. Maybe I'll draw my vertical line in yellow instead of. There's my vertical line. That's even hard to see as well. So is it a function? No. Why? Because every point fails the vertical line test. So that's kind of tricky, but you guys seem to have a pretty good handle on that. So I'm happy about that. That's a good thing. Looking at number 5. Number 5, what do we think? Yes or no, number 5? This one is pretty straightforward. I think you guys are pretty well on it, so I'm not going to belabor the point much, but if I draw a vertical line there, I end up crossing 1, 2, 3 times. So this is not a function. I have 3 intersections of my vertical line. Or vertical line test fails, not a function. How do you draw lines so straight? I have this thing, it's called a ruler, and has a very straight edge there. And I recommend you use a ruler at home as well. Or as I mentioned, use your calculator edge, and some of you guys have calculators with rulers built into them, which is just amazing. Technology's come so far. Calculator can do calculations and draw straight lines. There you go. Number 6. Can you draw a vertical line somewhere on that graph where you can intersect 2 points? We're going to go with number 6 is a failure of the vertical line test. Anyone else want to agree or disagree with Taylor? It's a failure. Let's not be hard on number 6 here. Let's go with it. Maybe fails the vertical line test, but it's not a failure. It's just a plot. All right, so if I draw a vertical line like right here, I'm only hitting 1 point, so that's good. But if I draw a vertical line right here, I've hit 2 points. And this one's a little different because it is, it's not a continuous line, it's a set of discrete points. So it just looks a little bit different, but the principle remains, vertical line test. If you can draw a vertical line that only intersects 1 point, you have a function. If it intersects 2, then you have a relation. So it fails. Vertical line test. So this is one of these ideas. What is number 6 trying to tell us? Looks really weird. Yeah, sometimes we just make stuff up that looks strange just to kind of prove an additional point. So we're talking about the vertical line test. If you're trying to, quantify that, what is that trying to describe? I'm not even sure what it would be describing. I can't even make something up on the spot right now. It's kind of that strange. So it's a good point, Alex. But kind of beyond what we're talking about, just the vertical line test in this example is all we're going for. So there you go. That was a vertical line test. Now, when you guys start, writing tests and provincial exams, and you get a vertical line question, you get a graph, and it says, "Is this a function?" And you just say, "Oh my goodness, a free mark. Thank you so much, math gods," because this is really that easy. There's nothing complicated about it. When we get into the next examples here, these ordered pairs, we really need to remember the difference between a relation and a function. So what I'm going to do is I'm going to jump back all the way to the very beginning of lesson 2 when we defined what a relation was. So we said a relation is a rule that associates the elements of one set with another set. So that was our relation. And then we went a little bit further and then we defined a function. Where did we define a function? I thought we did it on that same day. It's in there somewhere. Consider function, element, set, element. Am I losing it? Am I going crazy? A relation has a direction. It makes, what are the words? Graph equation. Northern relation, represent this relation, community. Oh, there it is. I didn't go down far enough. Sorry about that. A function is a special type of relation where each element in the first set is associated with exactly one element in the second set. So we looked at these 2 examples and it was kind of really weird. And the thing that kind of made the first example relation was this fact that 2, our first set is this first oval here. The 2 represented a bicycle and the 2 represented a motorcycle. So if I said, give me something that has 2 wheels, a bunch of you would yell bicycle, a bunch of you would yell scooter, and a bunch of you would yell motorcycle, and we'd be all really confused because the 2 could represent more than one thing. But if I said something like bicycle, how many wheels does it have? You would all say 2, because that's what a bicycle has. There was nothing in this second example, even though it was the exact same example just flipped, there was nothing in the first set of values that only gave you one value in the second set. So they all corresponded to one thing, whereas the 2 corresponded to 2 things. So keeping that in mind, we're going to jump into these ordered pairs here. Now this 7 should have been on the next page, another formatting error, but we have ordered pairs. So we have an x, y set of ordered pairs. The domain is the first half of our ordered pair. So is there, in example number 7, is there any number that comes in the first half that gives us a different y value in the second half of the ordered pairs? So let's take a look here. If I look at a 2, I get a 3, that's good. If I look at a 4, I get a negative 4, I get 5. 0 gives me 8, and 4 gives me 2. So there's no value that I've put into the first half, my x values, that gives me more than one y value. So that might not make a whole lot of sense right now, but we're just going to go with yes. And we're going to say that each x value has unique y value. And it might be worth writing down that when we have a set of ordered pairs, the first one is the x and the second one is the y. And when I say x value, this is what I'm talking about. And when I say y value, this is what I'm talking about. Just refreshing your memory from Math 9. All right, the number 8 is going to, kind of show my point a little more clearly. If the first one, 7, didn't make a lot of sense, maybe this one will. Now here, one thing that I notice is that I have 3 that appears twice. And when I say, okay, I give you a 3, and you're going to give me a 5, and then if I give you a 3, you're going to give me a 7. I'm going to say, which one is it? And you're going to say, well, it's both. And I'm going to say, well, that's a problem. If you like the vertical line test, you can think of it this way. If I plotted a graph and I said, okay, 3, 7, there's 3 right there, here's 7 up here. And then I said, okay, 3, 5 is right here. This is 7, this is 5. That is going to fail my vertical line test because if I give you an x value of 3, you're going to give me a y value of 5, and then you're going to give me a y value of 7. So if you want to think of it visually in terms of a graph, you can do it that way. If you want to think of it as an input of 3 giving you more than one output, then that's fine as well. So this is not a function, no. And the reason is 3 gives us 2 different values. So sometimes 3 gives us a 5, and then sometimes 3 gives us a 7. Is there something that isn't a relation or a function? I'm going to go with no. It has to fall into either one of those categories. If we're talking about like equations and things that we can plot on a graph, it's either going to be a relation or it's going to be a function. There's only 2 things it can be. Now that I've said it, you're probably going to find some obscure example that doesn't fall into one of those categories, but I'm thinking as long as you're plotting a graph, you're either going to have a relation or a function. Unless it's only one input and output. I'm not sure what you mean there. We could have a graph with just one discrete point on it, and technically speaking, that is a function. So there's nothing wrong with calling that a function. It's just one point. But it's still a function because it fits the definition of a function. I give you an input, you give me an output. I don't get the XY thing and how you're saying it goes into it. How come you didn't like the definition if you can draw a line without passing through? The definition I was going with, because of how I worded it, was untrue. It was true some of the time, but not true all of the time. When I took the inverse, or I flipped the definition to twice, then it became true all of the time. I was just kind of battling myself. So looking at the definition again, if you can draw a vertical line which crosses your plot once, then you have a function is how I originally had it. Now if I look at something like this, example 6 here, I could draw a vertical line that crosses my plot only once, and then technically speaking, according to the definition I had written, that would be a function, but that's untrue. So the definition I had written was true only sometimes, not all the time. So by flipping it, it became true all of the time. The XY thing, Taylor, how you're saying it, does it go into it? Not sure where you're going with that, but let's look at a couple more examples and hopefully it becomes a little bit more clear. All right, so 9 and 10 are similar to the ones we just did. We're looking for an x value that gives us more than one y value. Generally speaking, when you are giving a set of ordered pairs, if you see an x value appear more than once, guaranteed 99% of the time, unless it's a typo, if you see an x value appear more than once in a set of ordered pairs, it's a relation. Because they wouldn't write the same ordered pair twice. It would just be goofy to do that. If I look here, I see -1 appear once, I see -1 appear twice. In this one, it gives me an 8, and here it gives me a 3. I think that's maybe what you're talking about, Taylor. Taylor, kind of the way I'm processing it in my head is, I'm thinking of kind of we'll use this analogy later, like a computer, where I put in a value at one end, and then out the other end pops another value. So if you think of like a computer or a black box, and I say, okay, black box, -1, and it says, you know, it does its little computer thing, and it spits out 8. And I'm like, okay, -1 gives me 8. Perfect. And then, you know, I go through all these other values. 0 gives me 7, 3 gives me 4, and then I say, okay, computer, -1. And if it was a function, I should get 8 again. But because it's a relation, it gives me a different value for that -1. It's now saying, okay, 3. And I'm like, well, I'm confused. You just said it was 8, now it's 3. It's not a function, it's a relation. How does -1 give you 8? That's a great question. We're going to look at equations, the equations of lines and parabolas and all sorts of other stuff that you basically, well, let's just look a little further down our page here. This is an equation, and I can say, okay, what if x is 2? What does y equal, Taylor? And you'd go, okay, I can put a 2 in there. 2 squared is 4 plus 3. So when x is 2, y is equal to 7. And this is kind of what you did in Math 9. You probably had an equation, maybe not as complicated as that, but your teacher said, okay, make a table of values, x and y, and, you know, put in an x value. You put in x is 2, y gives you 7. What if x is 1? Well, now you have y is 1 squared plus 3. So 1 squared is 1 plus 3 is 4. Okay, so that's 4. So that is kind of the idea. With the ordered pairs up in 9 and 8 and 7, we don't know what the equation is, but they just give us these ordered pairs. So remember, we can represent these things lots of different ways. We can use charts, we can use graphs, we can use ordered pairs, we can use tables. There's lots of different ways where we can represent these things. So that's kind of where the numbers are coming from. Let's kind of stick with the idea. Spent probably more time than we should here. How do you find out if the number 11, if it is a function? That's a good question. Let's get there in a second. So let's get back to 9 here. So no, this is not a function. -1 gives more than one y value. So sometimes -1 gives us 3, sometimes it gives us 8. It is not a function. For number 10, is there any x value that gives us more than one y value? I have -2, -1, 1, and 2. So this is a function because each x value gives one y value. And generally speaking, as I said before, if you have an x value that appears more than once, if -2 showed up more than once, it's almost always going to be a relation. All right, number 11, 12, 13, and 14 are possibly, they're kind of moving to the edge of the types of questions you'll see. So generally speaking, the ones that we've done with like a simple plot and vertical line test or a set of ordered pairs, generally speaking, those are the types of questions you'll encounter. If they want to be really, really tricky, they'll probably ask a question like the ones we're about to do. So if you're good up to this point, that's excellent. You've got 90% of the stuff out of the way. 11, 12, 13, 14, 15, and 16 are all kind of ratcheted up a little bit in terms of difficulty level because they're expecting you to kind of know a little bit more about math. So if you kind of get lost in the next 6 questions, that's okay. Y is x squared plus 3. I wouldn't expect you to know what this looks like in terms of a graph, but in grade 11, you'll spend a lot of time looking at what this looks like in terms of a graph. So the only thing you can do as a grade 10 student would be to think really hard. Is there any number that you can pick for x that will give you more than one value in terms of y? So if you want to think of a table of values like I did here, you guys are familiar with table of values, hopefully, from grade 9. You spent some time talking about a table of values where you put in an x value and you get a different y value. So is there anything I can pick here for x that is going to give me 2 different answers? So you could, pick a bunch of Alex with these obscure questions. You could pick a bunch of x values and get a bunch of y values, and you could maybe plot a graph of what this thing looks like. If you plotted enough points, you'd end up with a graph that looked like that, kind of like a little smiley face maybe. Or you can just think about it. Was there anything I can pick for x that's going to give me 2 different values for y? If I pick something like 2, is it going to give me 2 different y values? If I pick a negative number, negative 2, is it going to give me 2 different y values? There's nothing you can pick for x that's going to give you 2 different values. So it is a function because each x value gives a unique y value. So there's no way of knowing for sure. That is true, Abby. Until you see a few of the kind of more strange ones, then yeah, that's going to be true. The best you can do for something like that is pick a bunch of x values and put it into the equation and see if it gives you different y values. We'll look at a couple more examples, and I'll kind of show you ones that are going to kind of trip you up. And you'll see ones that aren't functions, and we'll talk about why they aren't. So this next one's a good example. X equals y squared. We need to think about values. Basically, this equation always has to be true. So the right side has to equal the left side. So if I pick a table of ordered pairs, or a table of values here, what values can I give x that makes y true? Or you can think of it the other way. Let's think of it in terms of y values and x values. So if I pick something like x is 4, what does y equal? Y would equal 2, because if I resolve this equation, I've said x is 4, y is 2. I need to take the square root of y squared to give me y. I take the square root of this side, and I end up with 2 is equal to y. So that's all fine and dandy until we start dealing with some negative values. When I start taking negative values like negative 2, now I'm saying, okay, negative 2 is equal to y squared. I take the square root of both sides, and you're saying, oh no, you can't take the square root of a negative. So that just doesn't work. So we just can't do it. So what we end up with is a graph that actually looks like this, if you plotted it. And generally speaking, that is going to give you a function. So even though there's some values that don't work, for every x value you pick, you end up with a y value. What? That makes no sense. 4 squared is 16. 4 squared is 16, but I'm taking the square root, Alex. If I'm trying to get y by itself, I need to get, I'm not interested in what y equals, I'm interested in what, or sorry, y squared equals, I'm interested in what y equals. So even though there's no square roots in there, if I give you a bunch of x values, you need to give me y values. If I said x equals y squared and x is 16, what does y equal? So you plug in 16 for x. 16 equals y squared. Okay, how do I get y by itself? Well, I need to take the square root of both sides. Okay, what's the square root of 16? Well, that's 4. So 4 is equal to y. So if x is 16, y is 4. Hopefully that clarifies it a little bit. Again, this is a function. Each x value gives us a y value. All right. Just going to cruise through these last ones a little bit quicker. Y is 1/2 x minus 2. All right. Again, you don't really know what this looks like. We haven't dealt with lines yet. We will. We'll spend a lot of time dealing with lines. And this is the equation of a line. That is chapter 6, I believe, maybe 7. So there's no x values I can pick that's going to give me more than one y value. So this is a function because each x gives us one y. And if you don't trust me on that, you can plug in as many x values as you want, and you can get a unique y value every time. Number 14, y is equal to 1. The easiest way to describe this is to put it on a graph. So here's my graph, here's my x values, here's my y values. If I said y is equal to 1, you're like, okay, well, that's kind of weird, but let's go for it. So here's my y values, here's 1, here's 2, here's 3. If x is 7, y is equal to 1. So I have x is 7, y is equal to 1. If x is negative 200, what's y equal? Well, it equals 1. So y equals 1 is just a horizontal line. Doesn't matter what x is, y is always equal to 1. So in terms of my vertical line test, yes, this is a function because it passes vertical line test. Now, this is kind of a weird idea, and we haven't spent much time plotting graphs. So if you're kind of really confused by that idea, then it's all good. It'll become easier as we go through the rest of the course. We're kind of jumping a bit ahead of ourselves here. The same idea goes for this x is equal to 7. I have my x values and y values. This is x is 7, 1, 2, 3, 4, 5, 6, 7. All right, there's x is 7 out there. Doesn't matter what y is, x is always going to be 7. So y can be, 200, x is 7, y can be minus 200, x is 7, and I would have a relation because this fails the vertical line test. So it doesn't matter what y is, x is always going to be 7. This is not a function. Fails vertical line test. All right. Hopefully you've stuck with me thus far. This last one is kind of a tricky one. So if two x's are the same, it's relation. If we have two x's are the same, yeah, I guess that's kind of true. Well, if two x values give you the same y value, different y values, let's go with that, Alex. I think most of the time that's going to be true. This last one, I don't want to spend a ton of time on it, but I will tell you this. Once we get a little bit further into the course, it'll make more sense, but I don't want to get stuck in this stuff because we still have to do domain and range. X squared plus y squared equals 4. This is actually a circle. So if you plotted that on a graph, you're going to end up with a circle. I know that because you spend a lot of time studying it in Math 11 and 12. So this is not a function because Mr. B said so. And for now, that's going to be fine because I just want to move on. And I don't want to stick on this stuff for too long. We haven't spent enough time graphing for us to know how to graph that and come up with the ideas and things like that. So we'll just ignore that for now. Wouldn't 12 be a relation because x isn't a perfect square? When x isn't a perfect square? Wouldn't 12 be a relation? What if x isn't a perfect square? And then we just take the square root of it. We can take the square root of numbers that aren't perfect squares. We just end up with decimals. There's nothing wrong with that. So you can, in your own words, describe what a function is. Hopefully you... Oh, that's fine, Shayna. There's nothing wrong with that. I'm glad you asked the question. You can describe what a function is in your own words. Just, you've looked at a bunch, think about what it means to you. If you had to describe it to somebody else, what would you say? There's a few lines there. You can jot it down. I want to get on to this domain and range stuff. And Alex, I kind of skirted your question of how would you plot infinity on a graph? Because I knew we were going to come to this stuff here. And this is how. It's just, you were a little bit ahead of yourself again. Domain and range, all the x values, all the y values. Up until this point, when we talked about domain, we said, okay, we had like a set of ovals. And we said, okay, all the things in this oval are domain. Pardon me. All the things in this oval are our range. And it was just easy. If we had ordered pairs, the first thing was our x, the second thing was our y, the first thing was our domain, the second thing was our range. It was pretty straightforward. But now we need to look at a graph and say, if I'm looking at a graph, what is the domain? What is the range? How do I figure it out? So this is kind of the idea. Domain is the x values. When we have a graph, like letter A here, our x values are all plotted on this line here. And then we have our y values up there. So the horizontal axis is x's, the vertical axis is y's, and there we go. Now, Alex, to answer your question, to plot something that goes to infinity, what we do is we put little arrows on the end of our line. So on this line here, the top there's an arrow, and the bottom it's an arrow. And what that means is this goes on forever. Forever and ever that way, and forever and ever down that way. It'll never end. It goes on for infinity. So, if we think about, instead of a line, if we think about some ordered pairs, x, y ordered pairs. If I said, okay, x is going to be, 2 here. What's y? Well, that is 1, 2, 3, 4, 5, 6. So this is 2, 6. Okay, if I go up a little higher, I have an x value of 3 here, and 4 here, and 5 here, and 6 here, and 7 here, and 8 here. Are there any x values that this line will not use? If you want to think of it this way, if I drop a line down onto the x-axis, is there any x value that's not going to be used there?